Welcome back to the AI podcast series. This is the final video where we'll deploy our project to AWS and bring it to life in the cloud. If you've missed the previous videos, I recommend checking them out first to see how we've built and tested the project locally. Links to those are in the description below. Let's dive in. Before deploying, we need to make our app cloud ready. Specifically, we want to enable caching of models between runs to avoid fetching them repeatedly from Hugging Face. That's why we added the models bucket and download topic earlier in the project. Now it's time to integrate them. Let's start by opening the API PY file. This is where we'll make changes to integrate model downloading and validation. So at the top of the file, we're adding some more imports for resources defined in the common resources. These include the models bucket for storing our zipped models, the download audio model topic for triggering the model download, and these paths for managing model files, caching them locally, and zipping them for upload. So as these imports in place, we can start configuring permissions and setting up our topic subscriber. Next, we define the models variable, granting this service write access to the bucket. This permission is essential for uploading files to the bucket later. Then let's create a reference to the download audio model topic and allow this service to publish messages to it. This will let us trigger the model download process later. Then let's define the default model ID, pointing to Suno Bark. This ensures our service has a fallback value to use if a specific model isn't provided. Then let's add our topic subscriber. So let's start defining the function. This subscriber is attached to the download audio model topic. It will be triggered whenever a message is published to the topic. The first thing we do is extract the model ID from the incoming message payload. This tells us which model we need to download. Then let's start downloading the model. Next, we'll call snapshot download. We need to import this from Hugging Face Hub. This function handles downloading the model files to a local directory. First, let's set the repo ID to our model ID. We specify the local directory with our modal directory variable and the cache directory with our cache directory variable. And to ensure we only download the necessary files, we define a list of allowed patterns. These include the model weights, like PyTorch model.bin, configurations, tokenizer files, and others. As the download progresses, the directory path where the files are saved is returned. Once the download is complete, let's print the directory path to confirm where the files are saved. So let's start compressing the model files. First, we create a zip file using Python's zip file module. Let's rename the zip directory variable globally to zip path for improved clarity. Okay, moving on. We iterate through the modal directory and add all downloaded files to the archive. Each file is included with a relative path to keep the structure clean. And let's print out where our file is being archived. Finally, let's write the file bytes to the archive using the write method. When the zip file is ready, we use the upload URL method from our models resource to get a pre-signed URL for uploading the file. We open the zip file in binary mode and use Python's requests library to upload it to the bucket. Then after the upload is complete, we delete the zip file from the local system to free up space. Finally, let's log a success message to confirm the model has been cached in the bucket. By the end of this process, the model is zipped, uploaded, and ready for use in our project. Now let's scroll down to the post handler for audio file name. This is where we'll validate the requested model and pass its ID to the job. So first, let's extract model ID from the query string, defaulting to audio model ID if none is provided. If the query contains multiple values, let's pick the first. Then let's check if the model is downloaded. We'll use the models exist method to check if the model zip file already exists in the bucket. If the model isn't downloaded, let's return a 404 response with an error message instructing the user to download it first. So with that being said, let's add an endpoint to handle downloading models. Let's make a post request called download model, and this handler will publish a message to the download audio model topic with the model ID to download. So first, let's extract the model ID, and again, defaulting to the audio model ID. If the query contains multiple values, we pick the first. And finally, we publish the message to the topic, triggering the download process. Oh, and before I forget, since we're now checking if the model exists in the bucket, we need to grant this service read permissions as well. So we'll update the allow call to include read. And we also need to pass the model ID to the job, so we can use this later to download the model in the bucket. So now that the API service is updated to handle the model downloads and validation, it's time to move on to the batch service in podcast.py. Here we'll implement the changes needed to process the audio jobs using the models cached. Let's get started. We'll start by importing the models bucket. This gives us access to the bucket where our cached models are stored. Next, we define models and grant it read access to the bucket. This is essential since we'll be reading the models from the storage. Now let's move inside the gen audio job handler to update it. We'll start by retrieving the model ID from the job data so we know which model we are working with. If the model isn't downloaded locally, we'll copy it from the bucket. This involves getting a download URL, saving the file, unzipping it, and cleaning up. Let's add this step by step. Let's make sure we import the models directory and zip path at the top of the file, as we'll need these for the rest of the code. We first check if the model directory already exists. If it doesn't, we proceed to download it. We use the buckets download URL method to get a signed URL for fetching the model. The request get function lets us download the model content. Let's make sure the zip path exists. After that, we save the file locally to zip path. This ensures the file is ready for extraction. Then unzip the model to the local directory using the Python zip file library. Then we clean up by deleting the temporary zip file to save space. Finally, we'll update the logic for loading the model. Instead of downloading it from the internet, we'll load it directly from the local directory where it was extracted. So here we initialize the model using the bark model from pre-train method, specifying the local model directory. Let's also initialize the processor with the same variable. So that's all the changes we need to make to the podcast py file. With this, the batch service now fetches and uses the cached models efficiently. Next, we'll test it locally and make sure everything works as expected. So let's fire up the Nitric local environment with the Nitric start command and head over to the Nitric local dashboard. So firstly, let's test the audio file name route. I'll enter test as the file name. For now, this endpoint should validate if the audio model exists. Since we haven't downloaded the model yet, we'll expect a 404 response. Yep, looks good. So this tells us we need to download the audio model before proceeding. So let's go ahead and do that. We'll navigate over to the download model route and click send. So as a reminder, this triggers our subscriber, which downloads the Suno Bark model for audio generation. So let's switch over to VS Code again. Here you can see some logs showing the progress of the modal downloading. This part will take a little while, so I'll skip ahead to save you the wait. So that's all done. Let's go back to the Nitric local dashboard and validate that the model is in the bucket. So let's go to the storage page and click the models bucket. You can now see the Bark zip file in the bucket. This is our audio model ready to use. So it's time to start generating the audio. Let's go back to the API Explorer and click the audio file name route. I'll enter testing as the file name and input some text into the body. Then hit send. So back in the VS Code terminal, here are the logs as the audio is being generated. The service is processing the text and generating the audio output. So again, I'll skip ahead and then let's check out the file. So navigating in the .nitric run bucket clips folder, we can view all the files in the clips bucket. So there's a testing wave file in here. Let's go ahead and play the file.
Okay, this is cool, but let's wait and see what comes next.
Great, sounds good. So that's it for local testing. Everything is working as expected, and our model is successfully integrated into the workflow. Next, I'll set up a new Nitric stack and deploy this project to AWS. First, I'll go to my AWS console in the Sydney region. To run this project using GPU instances, we need to request a quota increase for running on-demand GNVT instances in the EC2 service quotas page. If you'd rather not use a GPU because your AWS account doesn't have GPU instance access by default, you can set the GPUs to 0 in the Gen Audio Job decorator in batches podcast.py. This way it will use only CPU resources. But bear in mind this will take a lot longer to generate audio from text. So let's search for the quota type, select it, and click Increase Set Account Level. I'm going to enter 8 as a requested limit, but you could set a number like 4 or higher depending on the project requirements. So I'll submit the request. The AWS approval may take some time, so I'll speed up the video here to the point where my request has been approved. To efficiently run AI workloads using GPUs in the cloud, we need to define our batch service runtime with necessary drivers and libraries. Let's start by creating a custom Docker file for our batch service. First, we create a Docker file named torch.dockerfile. Next, let's navigate to the finished repo. The link is in the description, and copy the contents of the Docker file from there. So in the builder stage of the Docker file, we install our project dependencies using UV. This stage ensures everything is set up correctly for our application. The final stage uses the NVIDIA driver for the Torch runtime. We need to specify the base image. We then install Python and execute our application. Let's also create a Docker ignore file to exclude unnecessary directories like .model from the build context. Again, let's navigate to the repo and copy the specified ignore files to prevent unwanted files from being included. Let's also update our Python Docker ignore file to ignore the .model directory, streamlining our build process. Finally, let's modify our Nitric YAML file to incorporate the new Docker file into our runtime, assigning the Torch runtime to the batch services. With these steps complete, we're ready to deploy our AI project to the cloud, optimized for GPU usage. So it's time to set up the Nitric stack. Let's use the Nitric stack new command and create a stack called test, and let's choose the AWS Pulumi provider. This generates a default stack configuration file. Let's go ahead and edit it to suit our deployment needs. So this is where we specify the provider, its version, and the deployment region. I'll set the region to Sydney. Make sure you choose a region near you that supports batch instances with GPUs. So if we scroll down to the optional configuration, first I'll customize the AWS Lambda configuration to better handle audio generation tasks. I'll set the memory to 1024 megabyte, the timeout to 900 seconds, and the ephemeral storage to 10 gigabyte to accommodate large model files and audio processing. Next, I'll add the batch compute environment configuration. So first, to do the batch compute environment key, this specifies how AWS Batch should manage the compute resources for our tasks. So let's do min CPUs 0 and max CPUs 4. This defines the range of CPU cores that the AWS Batch can allocate for our jobs. Setting min CPUs to 0 ensures no idle resources are reserved when there's no work to do. With max CPUs 4, up to 4 CPU cores can be assigned to a single job or spread across multiple jobs. Next, we have instance types. Here I've listed G5 as the preferred instance type because it supports GPUs, which are essential for accelerating model inference. The optimal setting allows AWS to choose the best instance in the G5 family based on performance and cost. Okay, so we're done setting up our stack config. Let's deploy. Since I already have my AWS account authenticated on this machine, I can deploy this stack using the Nitric up command. First, this builds our Docker images, then gathers the deployment specification and hands it off to the Nitric Pulumi provider. The deployment process outputs real-time updates as resources are created, such as S3 buckets, APIs, and batch jobs. So this will take a while, so I'll skip ahead to the final deployment result. And there we go, we're on the cloud. So Nitric provides the API endpoint and the resource group link. Let's take a quick look at the AWS resource group for our deployment. Yep, looks like everything's there. All right, let's start testing the deployment. I'll use Postman for this. So first, let's get that API endpoint and test the audio file name endpoint for validation. So as we remember from the local testing, this route checks if the model has been downloaded. So let's see if we get a 404 with instructions. Yep, looks good. So let's follow the instructions and call the download model route. Great, so this will download the Suno Bark model and add it to the S3 bucket. And here are the CloudWatch logs of the download. And here it is in the S3 bucket. So since the model is downloaded, we can move to the next step, generating audio in the cloud. So let's go back and call that audio file name route again. Let's use the test parameter and some text in the body. For this demo, we'll keep it simple with the test message, but remember the same setup powers the full podcast clip you saw in the first video. Now let's hit send. Great, we have a successful response. I'll now head over to the AWS Batch console and check out the job. Here you can see the job running, and I'll also open up CloudWatch to show some logs in real time. Once the batch job is complete, the generated audio file is uploaded to the S3 bucket. Let's download it and play it to confirm it works.
We did it. That's a wrap on our AI podcast series.
And that's it, guys. Our podcast project is now fully deployed to AWS, complete with GPU acceleration for high-performance audio generation. With this setup, you can take it even further by generating your own podcast scripts using an LLM, like Llama 3.2. If you'd like a bonus video on how to integrate it, let me know in the comments. I'd love to hear your thoughts and feedback. If you found this series helpful, don't forget to give the Nitric project a star on GitHub. And if you enjoyed the video, please like, subscribe, and hit the notification bell to stay updated on future content. Your support means a lot. Thanks for watching, and I'll see you in the next one.